Good morning, everybody. Today I'm going to be going through some worked examples from the road note. I'm going to look at four in particular: the Ashto design method, the TRL Sadaq, the TRL Overseas Road Note 18, and the DCP-DN. And we'll see how we get on. To begin with, we've made a decision. We've decided that we're going to build an earth, gravel or bituminous sealed road. And these decisions are made before we come along to design the road. So what decisions are required now? Well, obviously data must be collected, measurements made, gravel sources located, but these are not decisions. For example, traffic counts and axle weights are required to obtain the design traffic for all methods of road design, not just the ones we're dealing with here. And maybe a decision is required on the design life to use, but this is usually decided at the planning stage too. So let me remind you of one of the golden rules that I mentioned the other day. The first and most important point is that each method must be used in the way that the developers or authors of the method intended. This is really quite important and mustn't be forgotten. So let's move straight on to the Ashto method. The Ashto method is slightly complicated and it will take slightly longer than the others to deal with, but there are 6 design variables that you need to have the numbers or the answers to do a structural design. You need to know the design life in years. You need to know the design traffic, which is the cumulative equivalent standard axles in the heavily loaded direction during the design life. You need to know the subgrade strength in terms of its elastic modulus. You must remember that the Ashto method is an American method, so the units are not metric, they're imperial. So the subgrade strength in terms of elastic modulus is in terms of pounds per square inch. It's roughly equivalent to 1,500 times the CBR, so it's quite easy to calculate. We need to know something called the structural number, which I mentioned the other day, and then 2 factors that you're probably not so familiar with. It's called the reliability factor Z and the standard deviation of performance S0. So without more ado, let's get on with the design. The Ashto design equation looks very complicated at first sight. If you look at this on the screen now, you'll see that there are 5 terms only, which is not so bad. I've labelled what they are. The one on the left is the traffic. Layer thicknesses come into the structural number in the middle. The terminal condition is the level of roughness or smoothness or whatever way you decide the road is in need of repairs, and the subgrade strength is on the right hand side. Now, the fortunate thing is if we choose the terminal condition to be what is called a PSI of 2.7, that's pavement serviceability index, that middle term completely disappears and we end up with a much simpler equation. In other words, we now have this equation that has only 4 terms in it. So that makes it a lot simpler. The list of what those variables are is on the screen again to remind you. Right, we simply have to determine the value of these variables one at a time and enter them into the equation. The design traffic is fairly standard. I think you'll all be aware of how to do that. We need to know the numbers of vehicles and we need to know their axle loads, and it's a fairly standard method in all pavement design methods. The subgrade strength in terms of its elastic moduli, as I say, it's 1,500 times the CBR in pounds per square inch. The structural number and the reliability factor and standard deviation, I'll explain those in a moment and give you some numbers to put into the equation. So let's start. The first thing of all, the design life. For this particular example, we'll say it's 15 years. We have the axle load and traffic information, so we can calculate the traffic. And for this example, the expected traffic in millions of equivalent standard axles, W, is 0.45 million standard axles. The next item we need is the subgrade strength. In principle, the subgrade strength should be the weighted average of the subgrade strength for over the whole year, but correctly weighted according to the design equation. But this is actually quite complicated because the design equation is non-linear. So in general, people shorten this a bit, and so the best way is to take the wettest few months of the year and average those, and that's the example I've quoted. January, the subgrade CBR is typically 15%. The lowest value is 6% in October. The 5 lowest values are 8, 5, 6, 6, and 5, and that's an average of 6.6%. So as a fairly good guide, using 6.6%, that gives us a modulus of 1,500 times 6.6, which is 9,900 psi. Before we can calculate the structural number from the design equation, we have to choose the statistical variability factor S0 and the reliability factor Z. S0 is essentially the standard deviation of the empirical data that is obtained when we compare the performance of identical pavements over a number of years. Basically, it's a measure of the variability in performance that you get with real pavement design. Unfortunately, it is quite large. I think the range typically on the Ashto road test between the good performers and the poor performers of relatively identical pavements was about a factor of 4 or 5 in traffic. So that's a huge difference. So it's a very real problem with designing roads. Our measurements have shown it is typically 0.5 and often higher. For this particular example, we'll set S0 to 0.5. You'll see how that affects things in a moment. The Z factor is called the normal statistical deviate. In other words, it's if you remember your normal distributions, standard deviations, and so on, it's how you get your probability of reaching a particular value. If we set Z equals 0, we're basically dealing with the mean values. And obviously, if we use mean values, 50% of the time our road will fail before that, and 50% of the time it will last longer. If we set Z to minus 0.841, there will only be a small probability of this happening. It's effectively quantifying our risk. So for low volume roads, typically we would set Z at 0.841. This would give us a 20% probability of possibly not lasting the design life, but an 80% probability of exceeding it. So for higher volume roads, we would change that to 95% or even a 99% for very heavily trafficked roads. But 80% is fine for low volume roads. So we set Z equals minus 0.841, and now we have everything we need. We've got MR, we've got W, the traffic, we've got S0 and Z. And the best way to calculate the structural number is to use an iterative process, unless, of course, you programmed your computer to solve that equation for SN. But it's much easier to do it the other way around, have the equation telling you what W is equal to when you put these various numbers in, and plugging in structural numbers around 2, between 2 and 3, you'll quickly come to the result that to get a traffic of 4.5 million standard axles, you'll need a structural number of 2.52. Now we have to build up a road structure using the available materials. We haven't discussed materials yet, but Andrew has mentioned materials earlier in the lecture course. So let's press on. Strangely enough, and most people are a little bit surprised by this, the 1993 Ashto Guide for Structural Design of Roads does not recommend material qualities in the same way as most manuals. Most manuals will have specifications for materials in them. In fact, to quote the Ashto Guide, it says no specific quality requirements are presented in this guide. The specifications included in the Ashto Manual for Highway Construction are often used, Well, basically what we use is the specifications that we've been familiar with for many years, several years, that we've been using in our other design methods, and they are quoted in the manual in table 3.4 and 3.6. Also taking into account the issues of locally available materials that do not meet the old standards, but which Andrew has called appropriate. This is the table from the road note. As you can see, along the top line is the traffic classes for each road, and down the left-hand side is the subgrade strength. If you recall from earlier in this talk, the subgrade strength for design was 6.6% CBR, and the traffic level is 0.45 million standard axles. So there in the middle of the lookup chart is the specifications that we need for the materials, or for the road-based material. The plasticity index needs to be less than 12. The plasticity modulus needs to be less than 240, and it has to be of particle size distribution grading A, which is a good grading. So that's for the road base. If we look at the available materials, in this particular example, we've got gravel A, which has a plasticity index of 10, a plasticity modulus of 200, and a particle size distribution that meets grading or particle size distribution A from table 3.6, and that is shown to have a CBR with a specified density of 65 and to cost $40 per tonne. And that's labelled in green here because that basically meets the specifications. Gravel B does not meet the specification for road base. The plasticity index is slightly too high. The plasticity modulus is too high. The grading is grading B, which is not good enough for this road. And as you can see, the CBR is right on the cusp between one class and another, 60%. That is a cheaper gravel, $27 per tonne. And the third gravel C is weaker than the others. It only has a CBR of 35, a plasticity index of 14, and a plasticity modulus of 300. And that is adequate for capping, but it's not good enough for sub-base or for road base. And of course, if we really cannot find any local materials, locally available materials, last resort, we could possibly use crushed stone. That would be non-plastic, and as you can see from the cost, it is 2.5, 3 times more expensive than the others. So obviously using locally available materials is the answer to keeping the costs down. So we choose materials for the road base and sub base. The red fails the test, the specification test, the green passes. Therefore, gravel A for road base, gravel B is suitable for sub base, and gravel C is suitable as a capping layer if we need a capping layer. So we've now got all the materials that we could possibly use. We know what structural number we need. All we have to do is put these materials together in such a way that they create a pavement of structural number 2.5. Now, before we go on, it's worth checking to see if there are any other materials that might be suitable but less expensive. These are the materials that somebody has come along and said, we've got quarries for these, but it's worth asking around to see if there's anything cheaper. Always worth doing. The local people will know where other materials are available. Right, so this is the summary of the materials. The road-based material has a CBR of 65% at the design density and soak moisture content. It has a strength coefficient, according to the Ashto charts, of 0.12. The sub-base has a CBR of 35 and a strength coefficient of 0.10. The A1, A2, A3 coefficients are obtained from table 5.1 in the road note. All we have to do now is compile a pavement with an S structural number of 2.52. Now this is done essentially by trial and error. There's no There's no rules of thumb here. We obviously want to make sure that the layers are of the thicknesses that can be constructed easily, so they need to be thin enough to be compacted well, but not too thick that they cannot be compacted properly. We're all fairly familiar with the thicknesses that means. And so the next slide shows you, well, sorry, we have another effect to take into account, and that's climate. I apologise for not to mention that before. You remember from the lecture the other day that the climatic conditions are taken into account through these M multipliers that are used to multiply the strength coefficients. So in very wet conditions, the M values are greater than 1, which means that the structural number that you require increases. In very dry conditions, the M values are less than 1, so when you calculate the structural number, a lower value is needed to carry the traffic. So essentially, these are calibration factors for your local climatic conditions. I can't give you the answers for everywhere. You have to do it yourself. An important way in the original Ashto design method, they had something called a regional factor that simply multiplied things, multiplied everything, but that was not considered precise enough. So these multipliers, these local factors, are now the way it's done. Remember that the climate is not severe. We mentioned it very early on. The annual rainfall is moderate, so we set the M coefficients to 1.0, which in this example makes it fairly easy. Now, there are many combinations of layers and their thicknesses that can make up the structural number, but we choose thicknesses that are easy to compact well. The recommended design is as follows. The thickness of the road base, 175 millimeters. The thickness of the sub base is 200 millimeters. And the thickness of, we need a capping layer to get a structural number sufficiently high. And we need 250 millimeters of G3 as a capping layer. And this, if you can see from the sum, gives you a structure number of 2.49, which is close enough to 2.52 to be perfectly suitable. Now, this pavement is quite substantial and considerably thicker and stronger than normally we would consider necessary for a low volume road. Don't forget, I'm just applying the Ashto method. But the Ashto method has several ways where it can be calibrated based on local road performance experiments. In other words, although the way the Americans might use it is conservative and gives you a fairly thick structure, we can vary the, depending on climate, we can vary the M coefficients, we can vary the S0 term, we can design for a different level of reliability. So there are, as I say, 3 or 4 ways in which it can be calibrated for your local conditions, and that is what most users have to do. Now, that looks like a very complicated, relatively complicated design method, but most design methods are rather more user-friendly and easy to use. Almost all design methods can be used in what I've called desk study mode. You can use your design method to design many hypothetical roads to provide enough information to fill a whole catalogue of structures. So you can vary your subgrade strength, you can vary your traffic level, use the design method and come up with some structures. And then you put those structures all into your design manual, and they become very easy to use. What you need to use them is the traffic load, as you know, the subgrade strength for design, and we need to know about the available materials for constructing the road sufficient to protect the subgrade. So if we look again, a typical manual can contain most of what is just required on just a few pages. So you've done all the calculations in your desk mode. You've now summarized them all in your manual that can be literally 2 or 3 pages. There's an example. This happens to be one of the ones in the list. It's the TRL Sadaq design manual that was developed in Africa in the 1990s by my colleagues Tony Greening and Colin Gurley. As you can see, the traffic classes along the top, ranging from a traffic level of less than 0.01 million standard axles, in this particular case right up to 3 million standard axles. And you can see that in each little box there's a diagram of the structure you need, and down the left hand side is the subgrade strength. So literally, if you know the subgrade strength, you know the traffic class, and there's your design done for you. I mean, not done for you, but done by you in well advance of when you need it. So all you have to do is look it up. The different colored shading is clearly different materials, and as you can see, the thicknesses of the layers are clearly shown. Before we go on, I'd like to remind you that this is basically a CBR-based method. In fact, most of the methods that are in the manual are CBR-based methods, but we are also looking at the DCP-based methods. And the DCP method can be used in exactly the same way. A catalogue of structures like this can be built up instead of using CBR, but using the DN value. And the next slide shows exactly what that manual looks like. Again, the traffic is along the top, ranging from 0.01 million standard axles up to 1 million. The layers are down the side. The subgrade is essentially the bottom layer. And these numbers are the number of millimeters per blow of the DCP that material has to withstand. So those are maximum values. And that is exactly the same essentially as the previous slide. Instead of CBR, you have DN and the various layers down the side. So very simple. So to complete this little demonstration today, I'll prove what I've just said. I'll use the information about the traffic, subgrade and climate and materials from the Ashto example, and I'll design for 0.5 million standard axles in a moderate climate using the TRL Sadaq design charts. To use the TRL Sadaq guide, the only additional information that we need is that the subgrade needs to be assessed in a soaked state, and so samples are required that will be tested in the laboratory at the appropriate density and soaked. That is not to say that we believe that the subgrade will be soaked in practice. We're soaking the subgrade simply to classify the subgrade quality that we have for that particular road. You will recall that the subgrade strength in terms of CBR was obtained regularly in the previous example, the Ashto example that we went through. Testing soaked at the specified level of compaction gave a range of values. Now, we don't want to use the mean value because that means that half the road will be on a weaker subgrade. We need to use the 10 percentile so that 90% of the road is on a stronger subgrade than the worst 10%. So now we go into the catalogue, we have the subgrade strength and we have the traffic level, so we can find the recommended structure that we need very, very quickly. There is the catalogue of structures. The traffic level is, as we remember, 0.45 million equivalent standard axles, as shown by the green arrow, and the subgrade strength now, measured in the soaked state, is class S2. And so the structure that we need is 175 millimeters of road base, 150 millimeters of sub base, and a capping layer of about 150 millimeters on this relatively weak subgrade. And you'll notice that that is considerably thinner than the structure that we arrived at from the Ashto method. Now that example and the Ashto example were for new roads. In many cases, the requirement is to upgrade an existing road, and this requires a careful assessment of the condition of the existing road to determine how much can be incorporated into the new road. Most of the time, we hope that most of the layers can be included in the new road, but how much strengthening is required so that it can carry the new traffic level for the next 15 or 20 years, and we need to know how to actually design the strengthening. So the two methods that we would recommend, or we would show in the manual that are good for this, is the TRL DCP CBR method based on Rodner 18 and the DCP DN method. Both methods include an assessment of the existing road, and both are very similar in terms of testing materials, except with one major difference. The DCP-DN method does not use the CBR test at all. It replaces CBR testing and CBR values with DCP testing and DN values, including for the material strengths in the associated structural design catalogue that I showed you earlier. But basically, the use of the DCP allows you to get a lot of information about the existing road to make sure that when you strengthen it, you can get a really good quality road that will last a long time. That is the DCP and DN catalogue. As you can see, it's based those numbers in the rows and columns are DN values. As you know, a strong material requires a lot of blows to get through it. So these are limits. You must always have a stronger material than the values quoted here. Again, very simple to look up the chart. Obviously, when you're actually doing the calculations and looking at the existing road, there's quite a lot more to do, which will hopefully will be apparent to you when you try and do it, because both methods have an associated computer program that you can, I'm sure you could all use very quickly within a little bit of practice. And essentially that's it. Thank you for your attention.